Today we're going to be going over the fundamental counting principle, permutations, and combinations. So we're going to start with the fundamental counting principle, which states if one event can occur m ways, and another event can occur n ways, then the number of ways both can occur is m times n. Sorry, we don't have a lot of room here. Okay, so it's saying that if you have one event that can occur a certain amount of ways and another event that can occur another amount of ways, to find out the way that these both can occur together is to multiply. Okay, so in the morning, let's say you're getting dressed, trying to figure out what you're going to wear to school today, and you have 5 clean shirts and you have 3 pairs of pants. We can figure out how many outfits we can wear. This is the event M, this is the event N. So the number of ways they both can occur is M times N. So we would do 5 times 3, and that would give us 15 outfits. Now, in the past, you probably used something a little different. You've used probably what's called a tree diagram to represent this pieces of information. If we have 5 shirts, shirt 1, 2, 3, 4, 5, and we could wear each shirt with each pair of pants, pant 1, 2, 3, pant 1, 2, 3, and so on, for each shirt, each pair of pants, we would count how many different combinations we'd make over here, how many tree legs kind of we had over here, branches, and we would still get the 15. So this is just a more efficient way of making a tree diagram. So we're not going to make tree diagrams, but this is kind of the same thing that you would see if it was a tree diagram. So question number 1 says, police use photographs of various facial features to help witness identify suspects. One basic identification kit contains 195 hairlines, 99 eyes and eyebrows, so that means together in a picture is eyes and eyebrows, 89 noses, 105 mouths, and 74 chins and cheeks. Again, chins and cheeks are in the same, not 74 chins and 74 cheeks. Part A says the developer of the identification kit claims that it can produce billion different faces. Is this claim correct? So what we need to do is figure out how many different faces this kit can make, and then answer the question is if it's billions or more. So, again, fundamental counting principle. This is how much each event occurs, so all the events together, we just multiply. So we're going to do 195 times the 99 times the 89 times the 105 times the 74. So we multiply these numbers together. Whoops. Oh, what am I doing? 195 times 99 times 89. And we get 1.334998665 e to that 10. Now this e that you see here is that times 10. Okay, so that would be 1.334998665. E means times 10, and then the number next to it becomes that exponent. Okay, this is that scientific notation. This is how your calculator writes scientific notation. That just means either a really, really, really big number or a really, really, really small number. Our scientific notation times 10 to the 10th power means we're going to move the decimal place 10 places to the right because it's positive. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then if we have any extra spots, we fill in with a 0. So let's write this number. Just copy all the numbers first, and then we'll go back and fill in our commas to see if it's in the billions. So starting at the back, we go over 3, 3, 3, These are your hundredths, thousandths, millions, billions. So is this claim correct? Does it produce billions of different faces? Absolutely it does. Question B says a witness can clearly remember the hairline and the eyes and eyebrows of a suspect. How many different faces can be produced with this information? So out of all of the different choices, this person remembers the hairline. So when we go to hairlines and we look at hairlines, there is only one hairline that person is going to choose, the one that they remember that it definitely is. Same thing with eyes and eyebrows. There's 99 choices, but she knows exactly what eyes and eyebrows they were, so there were only one option for eyes and eyebrows. She does not know the person's nose, so she's going to have 89 choices for noses, 105 for mouths, and the 74 for chins and cheeks. So now we're going to multiply these 5 numbers together to figure out what or how many different faces she could create. So we multiply this together and we get 691,530 faces. So even if you know some of the characteristics of the suspect here, you still have a ton of faces to pick from. Question 2 says the standard configuration for a New York license plate is 3 digits followed by 3 letters. How many different license plates are possible if digits and letters can be repeated? So we have 6 things here, 3 digits and 3 letters. First thing we need to think about is how many choices of a digit do we have? If we think about a license plate, well, what numbers occur on a license plate? Any number from 0 to 9. So we count up and figure out how many that is. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 10 choices for digits on a license plate. So the first digit that this person can choose, he has 10 choices. Now, digits and letters can be repeated, so the second one, he will also have a choice of 10 digits. So he could have 999 or 444 or 000, okay? So third digit, he would also have 10 choices. Followed by 3 letters. How many letters are there in the alphabet? 26. And these can be repeated, so it could be AAA, LLL, MMM, okay, whatever letters. They could be the same letter, so we have 26 choices for each of those. So then we would take these numbers and just multiply all these together. 10 times 10 times 10 times 26 times 26 times 26. And we get 1757600. That's how many different license plates we have in this scenario. Question B says, how many different license plates are possible if digits and letters cannot be repeated? So now we cannot repeat letters or numbers. So the first digit that we have to choose from is going to be 10, because there's 10 digits to choose from. But now whatever number I used here, I cannot use again, so then I only have 9 choices for the second digit. And then whatever number is here and here I can't use again, so that leaves me with 8 choices for my third digit. Same thing's going to happen with letters. You have 26 letters to choose from the first letter, but then for the second letter you can't use the first one, so you only have 25, and then you would have 24. So then we would plug this into the calculator, 10 times 9 times 8 times 26 times 25 times 24. Then we get 11232000 plates.